Swayam Prabha. Digital India. Educated India.
Okay, so I have added a bunch of meshes here that I kind of sort of had readily available, and these are all surface meshes. One of these two femoral arteries probably has a boundary. I can't quite remember which one, and I didn't quite check as well. But there's a bunch of these meshes, and all the underscores are my kind of quick reference for how many vertices they have. There are a bunch of spherical meshes. Each of them has different number of vertices. So it's just a quick reference for it. And I have a bunch of these meshes. So part of this session is to try and do some basic processing with these meshes, and it's a little bit open-ended. So you are welcome to go around loading meshes and running some of these basic computations on any of the meshes from there. There is one caution that I might have to tell you, but probably not needed. We'll see. Okay, let's start by just loading this mesh for the sphere. So in my case, I'm running the notebook from this directory called demos. So I just have to load this is therefore the path to my meshes. Make sure you have the correct path to the meshes directory, and then nothing fancy. I'm just gonna change the path to the mesh every time I want to load a different mesh. No GUI click and select and so on. Okay. So I'm going to load this mesh, this 328 vertices. No, it's probably not vertices. It's 328 elements. My bad. It's 328 elements in the sphere. I'm going to load that small spherical mesh. Because I don't quite know if it's running or not. I'm going to redo this, but you don't have to. Okay. To just check if the mesh has been loaded correctly, I'm going to print the number of vertices and triangles, and something is not quite right here. Maybe I mislabeled it. It's likely that I mislabeled the sphere mesh. Okay, no big deal. And I'm going to visualize this, and this is the for me, at least in this demonstration today, this is the stickiest thing. The visualization is very basic, uses just Matplotlib's 3D axes and the trisurf to sort of plot it. You can't even rotate the mesh to sort of see that it's you have a static view. If you want, you can adjust some viewing specs. You could change the elevation, the azimuthal angle, and you can slightly adjust these viewing location. But this is very basic. Okay, so again, my intention is to convince you that you could use the Laplace Beltrami and do this quick and dirty demonstration. But in practice, hopefully you've learned a little bit of libIGL on Thursday or Friday, and maybe Thursday and Friday. And maybe you would learn a little bit of you might have learned a bit of some other graphics library, and you should be able to use something that is a bit more serious for actual processing. Okay, so that's the mesh of the sphere, and go ahead and try that. You can load the torus and the other meshes. Okay, so I just live debugged something. I was incorrectly printing the size, which is not what we wanted. We want to print the shape, and indeed each of them is labeled by the number of elements in it. So hopefully you have had a chance to load some of these meshes. So I mean, I would keep this a bit slower pace than this morning, and so let me know once you're done with notebook one, and maybe one or two things I can point out. Nothing's fantastic, but just basic guiding things that there's yet another mesh storage format that we use here. You might have learned about other formats, but in this I just use a very quote unquote naive and a very plain vanilla format where I have the vertices store the locations of the vertices of the mesh, and triangles contains the connectivity of the mesh vertices. So I assume that all elements are of the same type, no mixed elements, all elements are triangles in these meshes. So enough to specify their connectivity. And maybe we can look at a few of these. So these are a bunch of vertices, and this is perhaps for the femoral artery, and a couple of just viewing the first 20 triangles. So the triangles are all just connectivity, and the indexing for these vertices is assumed to start from 0. So that's the 0th index, and triangles therefore have some 0 index vertices popping up. Okay, nothing fancy, normal, small, like a very straightforward mesh format. So the only caution I was going to suggest is that it is possible that one or two of these meshes have triangles indexed from 1. There might be one or two. I think I've sat down and changed all my meshes to have indexing start from 0, but watch out. So sometimes this anything like setting up the Laplacian or something might fail, and if it fails, one quick check to do is to see what is the indexing here. So you might want to do something like ravel it and then take them in. And in this case, it's 0. In all of these meshes I've checked, it's 0, but there could be a mesh there. If this is one, that could be the reason why setting up the Laplacian could be failing. Okay. So these triangles are expected to be integers. So yeah, I mean, the connectivity that is expected to contain only integers for the library. So it's better to specify the D type to be int when loading the mesh. Okay, so maybe we'll wait another, it's till 240 for you to play around with this notebook, try loading some other meshes and visualizing them. You might want to change the parameters of this visualization, maybe change the coloring scheme or shading. I mean, there isn't too much to play around, and I'm assuming that everyone has some basic Python 3 on knowledge, so you should be able to play around with it. So I'll wait till for another 4 minutes before we go to the second notebook. But in the interim, if you have questions or want to share some thought or any follow-up on the lecture or even this notebook, please let know.
So Kaushik, the
Yes.
last mesh does it have a boundary?
Yeah, one of the two femoral arteries has a boundary. I think this one does have a boundary.
Right.
But that shouldn't be an issue as far as creating Laplacians on it goes. It's just probably not a watertight or mesh or something
Right.
like that.
Sure.
At least in this very crude visualization, I can already see that boundary there.
Okay, I have a quick question which may slightly be out of, you can say, what we discussed in the morning. So you were talking about boundaries. So there could be other problems where there are we have intermediate values given, and then some of the boundaries are not described. So it is partially well posed or something of that sort. So does the exterior calculus approach work in those cases? As in, does that stencil fit in?
Partial, okay, so partial boundary information for a PD is given, you mean?
Yeah.
Like
one boundary is
what's
given, and if the other one is like incompletely described, and we have some intermediate values instead, something of that sort.
okay? So okay, assuming it's a two-dimensional domain, let's fix that, not 1D. So you're saying part of the boundary, some values are given, but the
And,
rest, some information is missing.
yeah, and there is some compensatory information in terms of some other areas where the values are getting fixed, like a Dirichlet in between the inside the domain itself, but it is not a boundary.
So in such, okay, such problems can be a problem. So when you say that there could be interface values, there could be regions within the domain where you are forced to specify values, or you're given values based on whatever
Yeah.
problem you're solving. So this has nothing to do with exterior calculus per se. This is more classically just a question about, is such a problem well posed as far as PDs are concerned? And so I'm going to slightly throw my hands up here, because so I know there are probably other people who have more expertise in this. For instance, there are cracks. There are problems with cracks in domains, mechanical
Okay, I'll
cracks, for
tell
instance.
you my specific problem in that sense. Okay, it is like, say, if we have the heat equation in polar coordinates.
Yeah.
So there, what happens is we have a singularity, which we usually, as numerical folks, we don't really handle that well. So we create a pseudo boundary around that singularity. And we say we are going to, instead of taking a disk, we are going to take just a donut or something of that sort.
Okay.
Pseudo donut sort of thing.
You mean on a disk you puncture the hole or something?
Yeah. Because that hole actually is a singularity when it comes to the heat equation.
Only because you chose the wrong coordinates in some sense. It's a coordinate singularity, not really a heat equation singularity.
Okay.
So that's sort of there are problems with singularities in the solution itself. That's different kind of singularity, and that finite element exterior calculus can handle. But if you're like, for instance, you take spherical coordinates and try doing a problem on a sphere, you're going to end up with a singularity at the North Pole and the South Pole. Like in this case, something is going to be not well defined. But you could get away with it by putting so-called coordinate charts. You put two charts on the sphere, and the singularity kind of doesn't. You have to do some stereographic transformations, or you might have to put more charts and not do stereographic projection. There are ways to working around it, but it's not an intrinsic to the PD sort of a problem. There are such problems, though. Cracks was one thing, but you don't even need a crack. It's a very common textbook problem called reentrant corner. You have like an L-shaped domain. If you're a MATLAB person, the MATLAB logo for almost a decade or two has been the reentrant corner problem.
Okay.
So So yeah, so those you can handle. Those you have to take care of how you do the approximation spaces. But these kinds of problems, I don't know if there's like a one solution that fits all kind of an approach.
Okay.
And maybe people do it. I just don't know. I'm not familiar with such work.
Okay.
Okay, we are a bit past it. So hopefully everyone had no issues with the first getting started notebook, which means we can move on to the second notebook. Okay, so in this we are going to set up the Laplace Beltrami on at least one mesh. You're welcome to, then it's open-ended. You're welcome to try setting it up on a few more meshes, and we'll see what we can do with it. Okay, so I'm going to clear my output. Okay, so I'm going to just do this imports. I'm going to load the sphere, and this external package has a submodule called trymesh, from which there is a function called trymesh that you load, and you can pass trymesh. I think it's probably an object. You can pass it the triangles and vertices that you have loaded, and it'll set up an object. You can name it whatever you want. I've called it TM, and one of the methods for this object is a Laplacian matrix. And one of the choices for the Laplacian matrix is to set up the cotangent Laplacian. You have to say mode equal to half cotangent. Remember in today morning's discussion, there was a factor of half in the cotangent. It was half of cotan alpha plus beta. So that's where the half cotangent terminology comes from. And so you should be able to try setting this up and see what sort of a matrix it sets up. So this one sets up this is not such a reasonable thing, but it sets up a matrix which is really a numpy array, although many of the entries or most of the entries are going to be 0. It would be a better idea to set it up as a sparse matrix, but it's okay. We'll deal with this for the moment. So this package returns a Laplacian matrix, which does have the correct pattern that we expect it would have. This is its sparsity. It's kind of diagonal. Okay, I mean, there are other things because this is a sphere, not exactly a flat domain, but yeah, there's essentially a banded structure. So you're welcome to keep reading on, and you don't have to wait for me, but I'm going to wait here for a few minutes to try and see everyone has caught up to this. So this morning I was kind of saying this. I'll put it in the updated presentation when I put in links. But there are some really nice, you could use the discussion from today as a baseboard and use that to look for some sophisticated and even really well done lectures on discrete differential geometry encompassing the Laplace Beltrami and its discretization, for instance. Yeah. So one thing I was talking about this morning was Kieran Crane's discrete differential geometry notes, which covers, amongst other things, the Laplace Beltrami and does so in a very nice way. So where is the latest? Okay, here it is. So you search for Keenan Crane. I'll put it in the slides, of course, but if you want to go for it now or soon enough, you can try Keenan-Crane discrete differential geometry. And this is a pretty large document, I think maybe 100 odd pages, maybe. Yeah, so there are many interesting things here. There's the Poisson equation, discretization via FEM, via TeX, and other discrete differential geometry things which we couldn't talk about, or it wasn't part of our agenda anyways. So those are things maybe you could relate it with the things you've sort of seen in this course so far, some of them at least. Okay, so that's one place one reference I wanted to point you to. The other one I want to point you to is so there is a course in ETH Zurich on surface mesh processing. I'm blanking a little bit on the name of the course. Laplacian surface. No. Yeah, probably it was this digital geometry processing. No, shape modeling, and it's also called shape modeling and geometry processing. So this is another useful reference notes for some of this. I mean, this is from 2021. The version I knew of was the 2018 version that I was thinking about, but there are certain things here which are complementary to what I talked about. Let's see if they have something on. I think they have. Okay, they don't have anything in this edition. Oops, on Laplacians. The 2018 edition of this course had some stuff. So the thing I should search for is shape modeling. 2018. Yeah, this 2018 version of the course. And you can find like there's a chapter on the Laplacian. There's some chapter on deformation. In fact, okay, we'll see. So this is kind of different from what I mean, but it uses, so the Cotan formula is derived in this thing. It's to be slightly honest, this derivation is a bit involved and there are easier ways to stating it, but perhaps because they are going to give you the gory details behind all the background needed to deriving this Cotan formula. So the Laplacian Cotan is defined in this. You can take a look. But more interestingly, you can look at some of these remeshing, smoothing as application examples for things we learn today. So this is essentially, okay, this initial part is all about what good meshes are. If I remember correctly, one of them has Laplacian based, okay, not this, perhaps the deformation one has. Yeah, so there's smoothing by flowing. We want the notebook 3 is also a little bit of smoothing by flowing, but this contains more information which you can try to use or reproduce some of these computations on your own. Okay, we are going, so this has it for curves and surfaces. Then there's some, in fact, one of the third exercise we'll use this, but there are more examples that you should kind of look here. For instance, this is Desbrun et al. Their implicit fairing paper from SIGGRAPH 99, way back, I think. And then there's some smoothing via solving an optimization problem, which ends up, their notation is a bit weird, but this is the Laplace Beltrami, this is the mass matrix. both of which you have access to via SwayamPrabha or IGL or some other library. And when they say L, this is just the Laplace Beltrami with some mass inverse appended to it. Okay, you can, I don't have these are standard meshes, but I don't have the meshes for this armadillo and so on, but you could use this setup and try experimenting it on your own at your leisure later on. Okay, so those are some of these links I will add in the updated slides as a list of other additional material you can go look up. Okay, so let's do one other problem. Let me talk a little bit of theory, although this is really a demonstration session. I couldn't talk about eigenvalue problems at all in the main theory. So and Laplace-Beltrami eigenfunctions are used as Fourier basis functions in graphics processing. So it's kind of an important thing. So I didn't want to not talk about it at all. So let's talk about this problem. So in linear algebra, perhaps you already learned this week or know from earlier that this problem is called as the eigenvalue problem. So where oops, I shouldn't have done that. Where you have a matrix times a vector equals the scaling of the vector. Okay, so if this is on real domain, if the vector field as vector space's field is reals, then this problem is essentially one of scaling the eigenvector. And so the Laplace if we pick the Laplace Beltrami to be this matrix, we can find the eigenvalues and eigenvectors corresponding to the Laplace Beltrami, which in turn tells you something about the base space. I mean, you can use this is a separate linear. This has nothing to do with linear Laplacians and its discretizations. Just within the purview, within the realm of linear algebra, the if A is a symmetric matrix, all its eigenvalues are real, and if in addition somehow the eigenvalues are distinct, the eigenvectors form an orthogonal basis. Okay, if not, at least the eigenvectors will form an independent set, and you could therefore conceivably think of using the eigenvectors of a matrix, of a symmetric matrix, as a basis for Rn, for whatever purpose that you might want to use a basis for it. The symmetric is a little bit important because symmetry guarantees that symmetry is a necessary condition if you want for the eigenspaces to not be degenerate, and so the algebraic and geometric multiplicities are the same. And so at least for symmetric matrices, we can say something about using the eigenvectors as an independent basis for the space. So in the smooth setting, the eigenvectors of this problem would be really eigenfunctions. And you have a similar theory which says that for a self-adjoint linear differential operator or partial differential operator, the eigenfunctions of that operator are a basis for the space of functions. The space of functions here being the space of C2 functions, at least, because you're applying an eigen, like a Laplacian onto the functions. So this is therefore the linear algebra or the finite dimensional equivalent of it. Finding the eigenbasis for this Laplace Beltrami would help us in using those bases so using those eigenvectors as a basis. Okay. So I'm going to therefore use the linalg dense linear algebra package and compute the eigenvalues of this matrix, which has already been anyways specified as a dense matrix. Okay. this computation is just takes a fraction of a second on my computer at least, and then I'm going. This is just some visualization of these eigenfunctions, and since this is on this sphere, so these are eigenfunctions of the Laplace Beltrami on the sphere, and those are the so-called spherical harmonics, which are again themselves, they have had their use and they're probably still used. Okay, this is in increasing order. This is the eigenfunction corresponding to the first eigenvalue, and you can compute it and check what the eigenvalues are. So those are all the eigenvalues for this problem. You notice that the first eigenvalue is close to 0. So the Laplacian is really a semi-definite operator. It's all the eigenvalues are positive, which is what you would expect because it's a symmetric all the eigenvalues are real, which is because it's symmetric, but all the eigenvalues are also positive because the smooth Laplacian is a self-adjoint operator. But one of its eigenvalues is 0, and this was one of the things I referenced. This has to do with how many components there are in your domain. If your domain consists of a sphere, is multi-componented, which means it has a sphere and maybe a torus or something like that. The sphere is sitting in the space in between the torus. Then your eigenvalues would reflect on how many components it has. So at least the scalar Laplace, at least the Laplace Beltrami's eigenvalues, the 0 eigenvalues tells you how many components there are in your domain on which the Laplace Beltrami is defined. The corresponding eigenfunction or eigenvector is just the constant vector. So you can see this is kind of, you can't rotate it, but you'll have to believe that it's a constant vector. And then these are some of the other spherical harmonics. So it's an exercise, or you can try it now. You can try loading and computing the eigenvectors and eigenvalues for some of the other meshes if you wish. But caution, you might have to use the sparse library. So maybe I will just add a few here, and maybe I'll submit this notebook again to the Google Drive. Just a quick refresher in case you haven't used the sparse library. I have already loaded scipy.sparse as SPRS, and I'm going to set this up as a sparse matrix. So I can just say SPRS dot. There are many formats that are available for sparse matrices. This just is the so-called column major row format. And now you notice that L is set up as a sparse matrix. And you can then use the sparse linear algebra tools. .ix I think. Okay, my bad. So I am generally not a notebook person, so I'll have to. I like IPython's terminal interface because I can do things like more than convenience and comfort, or like more than like just being familiar with it. I can quickly check what is available. So okay, maybe I should do from scipy.sparse. Okay, so there is, at least I can see it's IXH. So I'm going to compute some evals and e vectors using using IX for this sparse matrix. And I can tell it how many eigenvalues I want. I can compute 10 of them, and then I can say like, I want the smallest magnitude.
पापा कैसे नहीं हुआ ये वाईफाई से किया है?
Okay, so this is not working. What attribute error? I see. Okay, and then it finished computing these. And you can notice that I'll let you do the analysis. This negative is a round off error. It's really 0, and you can compare which one's generated. How closely do the dense and the sparse solvers eigenvalues compare with each other? So I would just add this as a okay. So in case you want to play around with those sparse linear eigensolvers, you can go for it later. I've updated the Google Drive. Okay, let's now go to the, maybe I'll wait another 4-5 minutes and then we can go to the last notebook that I have for today. All right, let's now move on to the last notebook I have, which provides us some smoothing example using the Laplace Beltrami. And let me import the modules. Okay, I'm going to use the femoral arteries mesh to try and see if I can do any smoothing on it, whatever I can. And so on meshes, smoothing can be thought of, as far as I know, as a heat diffusion problem. Although I think I know of at least one other slight different variation of this theme, and maybe graphics people do lots of different variations on this flow theme to do smoothing. There are probably a bunch of methods, and I don't proclaim myself to be an expert in those methods. So you can always find out, or like maybe like people will know other techniques that involve the Laplacian, but is beyond just this basic heat flow heat equation like smoothing problem. Okay, so the problem, the basic textbook smoothing problem is that, okay, I move the vertices of the mesh. I think of it as heat that is flowing, and so I solve the heat equation with the vertices of the mesh and with the Laplacian, of course, because the heat equation involves the Laplacian. And here I've already slightly corrupted my notation, and I'm saying L is really the discrete Laplacian here, but think of this as coming from a smooth problem, and I am discretizing it and obtaining the scale like the Laplace Beltrami here. And I can discretize this using the forward or backward quotient. One of them will yield a implicit method, and the other will yield an explicit method. So for the backward difference, I would end up solving a linear system every time. And for forward difference, I'm just going to do matrix vector multiplications. Over here, I'm doing the easier version, which is matrix vector multiplication. I've set up the discretization of this, the d by dt of the vertices using forward difference. Yeah. So backward would imply I have to solve a linear system. Okay. So here is the femoral artery mesh. I did something. Okay. And I'm going to try and do I want to do 10 steps of smoothing, but let me start with at least one step. And let's see if I can, I have some arbitrary choice of parameters. Lambda is 0.1. I'm going to take a time step of 0.01. That's the step size for the discretization of the d by dt term. And I'm trying to be a bit careful in setting this problem up. So if I did the forward difference method, I would end up getting like a lambda L. Yeah, go on. So okay, if not, let me just quickly finish. So I would get a matrix which is like lambda dt L plus I into the vertices. So I'm just trying to be cautious here and changing the L from a dense array to a sparse matrix, and I'm setting up a identity matrix which is also sparse. Okay, and then I want to try doing one step of it to see if this indeed works. Okay, so one step was no problem. Okay, there is a small error here. I have to set this up, otherwise it's going to do nothing. Okay, so now if I do that, one step wasn't a problem. Let me try 5 steps. And that went through pretty quickly as well. So let me go ahead and try 10 steps.
Kaushik,
and
shouldn't
then,
the first line on the left-hand side should have an index 1 instead of 0?
Right. Thank you. Yeah. Thank you, Aditya.
No.
Here too, it was 2. I think this is 1. And I don't know where else did you mean?
No, so first line, the index should have been 1, isn't it? Because on the right hand side, you're taking V0 and you're using V0 to get V1, I'm assuming that.
And so this is the x coordinate that is being flown, then
Oh,
this is
okay,
the
we
y.
knew. Acha. Okay, okay, then it's
Yeah, and the z coordinate, yeah.
okay.
Okay, and then if I plot it, unfortunately this is bad. So okay, it's probably gone to 0 because the smoothing problem sort of collapses your mesh down. So you don't want to do too many steps of this smoothing. So maybe 2 steps and visualize what happens. Yeah, 2 steps, it's fine. Maybe if I did 5 steps, it's already, okay, it's already gone. This is some small value. So usually with this heat equation smoothing, my understanding is people do some number of steps of smoothing. And this mesh was quite reasonable to begin with itself. So smoothing is not going to really do much. But this is, again, the intent is like not to give you a noisy mesh so that you can smooth, which you could sort of set up on your own, but to quote unquote expose you to this idea that you can use Laplace Beltrami to perform a heat equation like smoothing of the vertices of a mesh. Okay. So you could try this with other meshes in the problem. And my one little homework for you, you're welcome to try other problems as well, but one little homework is I'll update the file here. So I'm going to say here we are going to use forward differencing, but for the dv by dt. But I want you to use the backward differencing, the backward quotient. I mean, I keep saying forward Euler, backward Euler, because that's what it's really called, but that's not language we have used. So I should say forward quotient and backward quotient. So I'm going to say we can discretize the time derivative using either the forward quotient or the backward quotient. And maybe for my own sake, I'll say these correspond to the forward Euler and backward Euler methods for one time derivative ODEs. So I think Vignesh was asking me about some stability, but here is the forward quotient is in time is not a stable discretization. So you have to take small enough time steps or time, steps. I did use time step, but the backward quotient is unconditionally stable with when you discretize a time derivative like this. So so as an exercise, you can.
Would this be a good time to talk about CFL criterion, Fourier filtering
Sure, we can talk
leading
about it.
is
Yes, maybe in 30 seconds we can talk about it. Exercise/homework. Please try smoothing all meshes using both forward and backward questions. All right, so I'm gonna put this as well into the okay, so the Google Drive is updated and yeah, go for it. CFL condition. Yes.
Yeah. No. I was asking, is this the context where it appears?
Not for the heat equation. No, the CFL condition appears for in the note I talked about the advection equation for the that's a transport equation. It's a 1D first order in time, first order in space PDE. Some would say that's one of the simplest first PDEs that you could encounter. That's the most simplest PDE, and it's in that context and in the so the advection equation is also a wave equation. So this is something that's important for wave equations, which are not so-called conservative systems. They are not in steady state. They are not dissipating, and in such problems, there is a important criteria called the Courant-Friedrich-Levy criterion for finite difference like discretizations, which sort of constrains how your spatial and time derivative can be chosen. So in the examples in the 2D example for finite difference for the Laplacian, I just said delta x and delta y can be equal, can be anything, can differ from one point to another. You don't have that luxury when you have a PD with time also being one of the independent variables, like an advection equation or a wave equation. It's not a problem for the heat equation, so there is no Courant, no
Okay,
CFL.
if it was in the Poisson format, then it would be a problem.
No, if it's so the Courant Friedrich, the CFL condition tells you you can't arbitrarily choose time steps and spatial steps. There's a relationship between them.
Yeah, there's a ratio, something that they used to do.
Right. And so for Poisson, there is anyways no time. It's a time independent PDE. So it is not even a concept for PDE for Poisson.
Okay.
Okay. But so that's for the smooth okay, that's for the problem. But in addition, your algorithm choice of method can also screw up your computation. And that's what this stable, unstable business means. Again, to talk about it would require, you can, like, there were many such concepts that kept popping up where it will take more time to spend on those topics to get a further understanding of it. So I would urge you to please go look up other material in addition to the references that I intend to put up. Google around or ask around and try and get a this one was really a very breadth first search type presentation today or a module. You can go very deep into many of those aspects.
Okay. Thank you.
No worries. Okay, so you folks, I hope you were able to at least run the code as this. If you're experimenting with some other meshes, go for it, and I'll hang around. And if you have something to report or share, let me know.